Hello, I'm going to see if I have time to create one little video for you about binomial theorem because you really should have learned this last year in the spring, and if you see it you might remember that you did. So the idea behind binomial theorem is that it's a shortcut using a sequence that allows us to multiply binomials together without actually having to multiply them. So to show you, I'm just going to use an example. Let's say, for example, we have x plus 3 and we need to multiply that together 5 times. So if we actually did that, we would start by multiplying x plus 3 times x plus 3, which would give us x squared plus 6x plus 9. But then we would need to multiply x plus 3 again, which would give us x cubed plus 6x squared plus 9x plus 3x squared plus 3 times 6 is 18x plus 27. Combine like terms, then we would multiply x plus 3 again and then again so that we have it 5 times, because this answer right here would only be 3 times, right? So it's just a way of making that easier. It's not necessarily easy. Oh, I wrote down the wrong number. But it makes it easier using a pattern. So here's what this would look like if we did it this way, right? X plus 27. So that is not finished because we would need to multiply that by the squared one, because so this one's cubed. So we would need to actually multiply that times this thing and multiply every one of those 4 terms in this problem times every one of the 3 terms in this problem, combine it all together, so we end up with 6 terms, starting with an x to the 5th, and then an x to the 4th, and then an x to the 3rd, and then an x squared, and then an x, and then a constant. So the idea behind binomial theorem is to save us mistakes and time and the struggle of doing such a problem this way. So to use binomial theorem, I like to use what's called Pascal's triangle. Pascal's triangle just comes from adding the numbers together in the next row above to get the next row down. So you just start with ones, and then like 1 plus 1 is 2. So then for our next row, we start with a 1, and 1 plus 2 is 3, 2 plus 1 is 3, and then we end with a 1. And then our next row, we start with a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and we end with a 1. In the next row, we start with a 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, we end with a 1. And then, actually we can stop there, but this pattern keeps going forever. The reason we can stop there is that because we're doing a 5th power, we would use this row right here for binomial theorem. These numbers can also be obtained by using what's called combinations, and that notation is in your textbook if you'd like to look at that closer, or probably in the video provided by the University of Utah. Okay, we're going to do this using binomial theorem. So to do that, we have x plus 3 to the 5th power. We're going to start by our first term being x to the 5th power, but then we need to factor in that 3 with the 3 to the 0 power. That really doesn't honestly matter. I probably didn't need to write that at all, because 3 to the 0 power equals 1. And 1 times x to the 5th is just x to the 5th. So why did I write that? Well, just so we can see the pattern that's going to happen here, okay? So then our next one would be x to the 4th, 3 to the 1st power. And then next we would have x to the 3rd, 3 to the 2nd power. And then next, probably put the plus 2 first. I'm going to put the plus, you'll see why in just a second. Put the plus over here. And then next we would have x squared and 3 to the 3rd. And then we would have x and 3 to the 4th. And then last we would have, and I've run out of room, x times 3 to the 5th. Okay, right now that's all jumbled, so let me fix this just a little bit. Move things over a little. That where that goes. Move that whole thing. That will work. And then the other thing I can do is, I don't like this whole mess, so we're going to take this thing and shrink it out of our way. That was just for demonstration purposes. Okay, so I did start getting smaller as I went along, so maybe I'll just grow that a little bit so it's all a little bit more consistent. Now remember these numbers down here? I'm going to go ahead and keep the red color I highlighted them in, because those numbers are going to go here. 1, 5, 10, 10, 5, 1. And the reason I know that those are the numbers is because it's a fifth power, so it goes with the 5. So that's the fifth power. We use that row of Pascal's triangle. Alright, then something else I want you to notice about these exponents. So 5 plus 0 is 5, 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5. This would technically be 1, I didn't write that. 4 plus 1 is 5, and then this one I messed up, should have been a 0, and 0 plus 5 is 5. So one of my terms, the exponent, is starting at 5 and going down to 0. The other term in the binomial is starting at 0 and going up to 5. And as that happens, the two exponents together are always going to add up to that 5. Now it's 5 because this example is the fifth power. If it were the sixth power, they would add up to 6, and we would use the next row of Pascal's triangle. If it was a 4, they would add up to 4, and we would have used the previous row of Pascal's triangle. So it's all in that pattern. So now that we have this, let's go through and calculate out some things. So 3 to the 0 power is just 1, so I don't even really need that. 3 to the first power is 3, 3 to the second power is 9, 3 to the third power is 27, 3 to the fourth power is 81, and 3 to the fifth power is 243. Now that we've kind of written those numbers out, we can combine everything together to get our final answer. So we have a 1 times an x to the fifth times a 1. That just gives us plain old x to the fifth. Next we have 3 times 5 times x to the fourth. So that's 15x to the fourth. Next we have 9 times 10 times x to the third. So the 9 is this 3 squared, right? I rewrote it down there. So 9 times 10 is 90, and then x to the third. And then next we have 10 times 27, so 270. That's instead of that 3 to the third, because that's 27. X squared. Then we have 81 times 5 times x. So that will be, I think it's 405, because if it was 10, it would be 810. So half of that is 405. X, and then last we have 243 times 1, because technically that x to the 0 turns into 1. So 1 times 1 times 243. We have now found the binomial expansion of x plus 3 to the fifth power by using Pascal's triangle, otherwise known as binomial theorem, without having to keep going on this process and multiplying everything out and all the mistakes that might come from it.